Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Have you ever wondered why your internet seems to lose its spirit the moment a heavy rainstorm begins? It is a phenomenon that bridges the gap between the abstract world of mathematics and the physical reality of our atmosphere. We call this the Shannon Cloud. To understand it, we first had to meet the father of the digital age, Claude Shannon. In 1948, Shannon published A Mathematical Theory of Communication, which changed everything. He gave us a formula to calculate the absolute maximum rate at which information can be transmitted over a communication channel with zero error. This is known as the Shannon limit. This limit is defined primarily by two factors: bandwidth and the signal-to-noise ratio. If you want more data, you either need more bandwidth or a significantly cleaner signal. In our modern world, we are chasing higher and higher frequencies to obtain that bandwidth. 5G and the upcoming 6G networks use millimeter waves. These waves are tiny, and that is exactly where the trouble starts when the clouds open up and the weather turns. Think about a raindrop. In children's books, they are drawn as perfect little tears with a pointy top. In reality, the physics of fluid dynamics is much more interesting. As a raindrop falls, air resistance pushes against its bottom, flattening it out. Large drops actually look more like hamburger buns or flattened oblate spheroids than tears. This geometric complexity is a nightmare for high-frequency wireless signals. When a high-frequency electromagnetic wave hits a falling raindrop, it does not just pass through unimpeded. Because the raindrop is roughly the same size as the wavelength of a 5G or satellite signal, it triggers something called Mie scattering. The raindrop acts like a tiny, chaotic lens and prism combined. It absorbs some of the energy, heating up the water ever so slightly, and scatters the rest in directions far away from your phone's antenna. This is what engineers call rain fade, but the Shannon Cloud concept takes this further into the realm of pure information theory. But it is not just about the signal getting weaker. The specific geometric complexity of the rain is the real kicker. Because raindrops are flattened and not perfectly spherical, they affect the signal differently depending on whether the wave is vibrating vertically or horizontally. This is known as differential attenuation and phase shift. If a 5G tower is sending data using polarized waves to pack more information into the same frequency, the tilted, falling rain can actually rotate the signal, causing the data streams to crash into each other. This creates a massive amount of noise and interference. Referring back to Shannon's fundamental formula, when the noise goes up and the signal strength goes down, the maximum capacity of the channel, the air between you and the tower, plummets. This is the Shannon Cloud, a theoretical ceiling on data transmission imposed by the physical state of the weather. The specific interaction depends on the relationship between the wavelength and the particle size. In the Rayleigh scattering regime, where particles are much smaller than the wavelength, like oxygen or nitrogen molecules, the loss is minimal for radio waves. But rain sits squarely in the Mie scattering regime for modern high-speed data. Here, the raindrop's cross-section for scattering is at its peak. It is almost as if the raindrop is specifically tuned by nature to block our most advanced communication frequencies. Furthermore, the turbulence of the wind adds a temporal dimension to this complexity. The raindrops are not just static obstacles. They are a moving, vibrating, and colliding medium that changes the Shannon capacity of the air millisecond by millisecond. This makes it incredibly difficult for hardware to adapt in real time. As we move towards 6G, we are looking at even higher frequencies, like terahertz waves. At these levels, even light fog or high humidity can start to act like a solid wall. The geometric distribution of water molecules and droplets creates a fractal-like barrier. Every drop added to the atmosphere is another variable in a complex equation of interference. Scientists are working on ways to punch through this cloud. One method is adaptive beamforming, where the cell tower uses artificial intelligence to constantly reshape the signal to find the gaps between the raindrops. Another is MIMO, multiple input, multiple output, which uses dozens of antennas to send the same data over different paths, hoping one will make it through the storm unscathed. However, no matter how clever our engineering becomes, we can never break the laws of physics or the Shannon limit. The Shannon Cloud reminds us that even our most advanced digital dreams are still tethered to the physical world and the geometry of nature. The next time you are stuck in a storm and your video starts to buffer, remember that you are witnessing a fundamental battle of physics. You are standing inside the limit of what the universe allows information to do. The raindrops are not just water, they are tiny physical barriers to the infinite flow of data. For more incredible facts like this, don't forget to subscribe and turn on notifications.